Okay, hello. So this is Andrew Coe, and this is my physics project, my final physics project, and it's a presentation on the effects of physics on competitive swimming. There's a picture of someone swimming with a velocity graph. So, start. Buoyancy and Archimedes' principle. Swimming has many resistances, and the forces of water can be much crueler than land because of water being 773 times denser than air. So how is floating possible on the water if we can't float on air? Archimedes' principle. Archimedes' principle states that if an object submerged under fluid, the buoyant force acting upon the object is equal to the weight of the fluid that was displaced from the object. This means that when you submerge yourself underwater, the water will seem to push you back up to the surface and your body will feel much lighter, and that is buoyant force. This occurs because pressure increases as the depth increases, so the lower part of the object increases greater buoyancy due to the more submerged part of the object, or the lower part experiencing more upward force because it's lower in the water compared to the upper part of the object experiencing the downward force is less, and that downward force is lesser because it's higher up in the water, so it's less dense. So this causes buoyant force to propel you upwards as you swim, and to become more buoyant, swimmers use their upper body since it is the body's center of buoyancy, because that's where your lungs are, and also lungs are filled with oxygen, and it's also the area with the greatest surface area. So the upper body needs to be used effectively and efficiently because the lower body will sink and not be streamlined, and that'll cause eddy resistances that I'll talk about later. And the swimmer needs to be parallel to the surface. And in order to do this, the chest will be pressed down and the hips will rise, sort of like axis of rotation. Like say like your chest is like the axis of rotation, and like one side is tilted and the other side is it's not balanced, so you obviously push your chest down to bring your hips up. Anyways, the higher the swimmer is in the water, the less water they're swimming through, and obviously moving through air is a lot easier and a lot faster than moving through water, and that lets the swimmers to go faster. And yeah, so another force that we see is surface tension. It's important to be streamlined as possible while staying underwater during the underwater phase of swimming. And let me explain real quick rundown. There's different phases of swimming: the diving phase, the underwater phase, and the swimming and the turn. And in the underwater phase, you're only allowed to go 15 meters, and it's important to make the most out of those 15 meters. And the reason why is because of surface tension. Surface tension, as we know, is caused by the surface molecules, H2O molecules, whatever fluid, being more tightly compressed together with less distance between them due to the intermolecular interactions. Surface tension takes energy to break and is also not as efficient as staying streamlined underwater. When the water is able to flow smoothly, uninterrupted over the body, also known as laminar flow, it creates the least amount of resistance. Stroking at the surface is constantly breaking that surface tension and disrupting that laminar flow, and that causes lots of drag and slows you down. And since water also provides many resistances, it's better to kick underwater and propel yourself rather than kicking the air. And this little drawing that I made in MS Paint, these are just H2O molecules being pulled down by other H2O molecules to show surface tension, since the surface H2O molecules aren't experiencing any upward force, only downward force, because obviously there's no H2O molecules up here. So Newton's law and friction. So Newton's law, as we all know, an object in motion will stay in motion unless acted upon. An object at rest, same with object at rest. So how does this relate to swimming? This is fundamental rule, and you need to respect it while swimming. So that means you will remain motionless, or you'll continue in velocity as long as the propulsive force is greater than the resistive force, or if the resistive force is greater than the propulsive force. So Newton's second law states that force equals ma, mass times acceleration. So how does that relate to swimming? Every portion of a swimmer's body is subjected to a variety of forces, and to make things easier, we'll look at the swimmer as a whole, and we can look at this free body diagram, and it shows all the forces that the swimmer that acts upon a swimmer underwater, and we can see the propulsive force, the resistive force, and then the buoyant, and then the gravitational force. Those are canceled out. So our equation is F net is equal to propulsive force minus resistive force, since the swimmer only swims horizontally. So how do we go faster with this knowledge? And we'll continue, and let me just continue on with Newton's second law and third law. So in swimming, the force produced by a swimmer is equal to the mass of the swimmer multiplied the acceleration, as stated earlier. And Newton's law explains why some people swim faster than others. If we have two swimmers of the same weight and have them push off a wall and not take any strokes, the one who used the most force pushing off the wall would be the person who has traveled the furthest. Acceleration in this case was greater for the person who produced the greater force, as both swimmers had the same mass, obviously. So, for example, swimmers both have a weight of 80 kilograms. One takes off with an acceleration of 1 meter per second, and the other takes off with an acceleration of 1.5 meters per second. So, F equals 80 kilograms times 1 meter per second equals 80 newtons of force. And person 2, they have 120 newtons of force. So that shows that obviously person 2 push off the wall with more force, 40 newtons to be precise. And Newton's third law relates this concept to the standard hand-arm stroke, when the hand travels downward in the water and then backwards to propel the swimmer forward, in creating an equal and opposite reaction. And the swimmer is kept afloat and propelled forward, just like Newton's third law says. If you push onto something, it'll push back with the same amount of force. So, how do we go faster with this knowledge? So, technique and drag coefficient. Technique is extremely important because it's the main way to reduce frontal drag, and we all know that drag is the main thing that slows us down in swimming. So, and it's the main force acting upon you in water. So frontal resistance occurs when the body rides too low in the water, essentially producing a larger surface area that pushes against the water in the direction opposite of forward motion. To limit the effect of frontal resistance, the swimmer tries to position themselves as high in the water, similar to a hydrofoil, like this picture above here. And swimmers will also roll their body from side to side in conjunction to this as swim strokes are executed, and this turning movement will help keep the body higher in the water, and the rotation of the shoulders also produce significant energy during the pull. And let me play a video that explains why. I might skip ahead a bit on this. Sorry. Okay. Anyways, I go on a little tangent, just like spinning my shoulders, so that's not needed. And anyways, the technique will allow you to be more efficient in the water, allowing more water to be pulled. This frontal drag can be calculated with force. Force of drag is equal to 1/2 density times cross-sectional area times the drag coefficient times velocity squared. So the first variable, P, represents the density of water. The second variable is the cross-sectional area. The last variable is the drag coefficient. This variable takes into account how water interacts with the object, and it depends on the shape and the surface of the object. The drag coefficient will cause a dramatic change even with a small difference, and I gave a little example here. So we utilize the front drag equation and do a little algebra with the power equation to solve for velocity. So V equals 2P over PAC power 1/3. And oh yeah, and something very important is if the water temperature is higher, the density decreases. So that causes the swimmer to be less buoyant and the swimmer swims slower. So that's why all competitive pools are kept at a certain temperature, which is usually around, I don't know, like, I'm gonna go on a limb and guess, but like around 70 degrees or so. I'm not sure, but it's usually cold. It's definitely cold, not hot. So yeah, that's the importance of water temperature. And then anyways, if we were to change the drag coefficient by 0.01, we change our velocity from 1 to 1.0034, and that's a increase of 0.34% increase in speed, and that's very minuscule, but in swimming, races are decided down to the 100th, and these minuscule things can honestly make a huge difference, and that's the work. Anyways, oops. So, more ways of decreasing the drag coefficient. Shaving. So, swimmers shave before the competitions. So, skin friction is a kinetic friction of the swimmer skin with the water, and this is solved by shaving the hairs from the body. And a swimmer can either shave or wax their body hair, and that decreases the surface area of their skin. And I don't know if anyone waxes, that's not common, but this is Caleb Dressel, probably the fastest man who swam ever, and he still swims, and you can see he has a mustache and lots of hair. And now you can see, this is Tokyo 2022 Olympics, you can see no mustache, no armpit hair. He has chest hair, but he shaved that all. And obviously why? Because shaving decreases the drag coefficient, and as seen before, even a small amount will make a huge difference. So, and other ways of decreasing drag coefficient. So tech suits or racing suits are used by swimmers only, like usually when you race. So these suits are designed specifically for when you race, and they mimic the characteristics of shark skin. And the surface of the suit is like constructed with a series of ridges that tend to reduce drag because the ridges deflect the water away from the surface. So a little history lesson. These are the super suits, or the shark skin, the full body suits that were worn by both male and female. Only females now, but the males used to wear this up until 2009, and the reason why swimmers don't wear this anymore is because of both sponsorship issues and also ethical issues, because these suits, they decreased the drag coefficient so well, and they also made the swimmers so buoyant and also very streamlined in the water. So these suits, they were worn once, at Olympic Games, and boom, I don't know how many world records were broken, but a lot were broken. So there was lots of discussion, of course, and these sort of suits were only manufactured by certain companies. So obviously, swimmers that weren't sponsored by these companies were at a disadvantage. So there were these concerns and discussions. So current day and age, males wear this sort of suit, so it's only waist down to the knees, and females still wear the same thing. So yeah. So eddy resistance. So as mentioned before, eddy currents occur when a fluid is in a laminar flow, but there's a turbulent flow in the back due to disturbance. And this disturbance can be anything, but in swimming, this disturbance is caused by poor stroke technique and riding too low in the water. As talked about before, it's important to stay high in the water. So that causes lots of frontal resistance. So the water is unable to fill in instantly behind the swimmer, and that causes them to pull water and air bubbles along with them, and that slows them down because it causes drag. And whenever a swimmer executes a freestyle stroke or front crawl, an eddy shaped as a vortex or whirlpool forms at the water surface, and if the stroke isn't executed properly, the vortex will remain, and if the vortexes accumulate around the body of the swimmer, the water resistance is increased. So that's why, like, I don't know if you noticed, but sometimes there's these old people swimming in the pools and they're swimming really slowly, and the reason why is because they're riding really low in the water. And as you can see, this shows the importance of why it's important to stay horizontal and not at an angle or vertical. So coupling. Coupling is when two axes in movement interact with one another, and in swimming we can use coupling to increase velocity and momentum in the water. And here's a little video of me explaining my breaststroke. Let me see if I can speed it up. Okay, so yeah, so that was the video on coupling, and then oops, okay, and then now here's the turn. The turn is when you're swimming, you convert your linear momentum from swimming into angular momentum into the wall, and you use the equation, the angular momentum equation, and obviously the fundamentals apply here, even in the water. The tighter the radius, the greater velocity, since mass and angular momentum doesn't change, and just like the figure skater, the tighter the radius of their spin, the faster they spin. So just like the tighter the turn, the faster you'll turn. So just like in this video, I record myself swimming freestyle, doing a flip turn. So I did a little side-by-side comparison of doing a tight turn and a non-tight turn, and this is what the difference. That's the difference between a tight turn and a non-tight turn. Obviously, the tighter turn is much quicker than the non-tight turn. Touches the wall first and leaves the wall first. Simple as that. Okay. And then the dive. So the dive is the beginning of the race, right? So that's the most important part. And this little image shows how you can utilize gravity on the dive to convert your horizontal movement into the dive, and also utilize gravity to gain as much velocity as possible into the water. So let me play a little video explaining the dive also. I can't seem to put this in full screen, so that's a little unfortunate, but I'm going to speed it up. Hole. I said hole. Oops. Okay, wait. Sorry. So, very simple, how to increase your propulsion thrust. You get stronger, you lift weights, or I don't know, you get taller. That's why a lot of swimmers are like 6'5", very tall. And yeah, that's my presentation. Thank you for listening.